Hi everyone, today is our turn to give the workshop presentation. Our topic is virus spreading, simulation, and potential risk detection, COVID-19, the novel coronavirus. Our group member is Zichaofeng, Dan Rongjiang, Jin Liyan, and Peng Zheng. Our presentation includes 5 parts: introduction, back-end implementation, testing data design, front-end techniques, and future plan at last. The first part is a brief introduction to our project. As we all know, the COVID-19 is spreading all over the world now. Wish everybody stay home and stay healthy. There are millions of people have been infected since the COVID-19 outbreak. Under such serious situation, we want to do something to help. So this is the main idea of our project. There has been lots of applications related to COVID-19. However, the backtracking of infection is difficult through social media. We need an effective method to help people know if they are in dangerous situation. Our project's goal is to establish a platform to help people check their infection probability. We will provide a network model to calculate this and give people the useful information through our website. Then I will introduce our system components. The system has a network to simulate the virus spreading, a data store to store everyone's information, a web service for everyone to interact and use.
Okay, let me introduce the back-end part of our application. We start with the architecture of our application. Users raise HTTP requests through their web browser. Our front end will collect those requests and send them to the backend. Then the application server, acting as a hub, will process these requests based on our program. Here we use Google Cloud App Engine as a platform where we deploy our codes to maintain our web services. Google Cloud Data Store is used for storing our data. When necessary, we could fetch essential records from it to do infectious probability calculation or response to the related requests from the client. Let's take a look at our application server. Our application is implemented based on representational state transfer web service architecture. Under such architecture, only basic HTTP methods like GET, POST are used, which makes our application lightweight and easy to maintain. What's more, as an important feature of REST, all resources are identified through their URIs. It's possible for users to get access to our service anywhere, anytime with internet connection. And unique identifiers for different users make users could only get access to their own resources, which makes our system very secure. Here's an easy example of how REST Web Service works to insert a travel record into our database. The server receives POST requests from client along with the unique URI travel here. Then the server will execute our codes and do something to put the record into the database through the API the database provided. Flask is used as the web framework of our application. The API's Flask provided is consistent with REST architecture. For example, here's part of our program implementing the travel info entering page. Our application will route users to the corresponding page through URLs. Then the server will execute our code. If the user posts a HTML form containing the information he or she enters, our backend will collect those data and store them into the data store. As we mentioned above, we use Google Cloud Data Store as our database. It's a non-relational database where data is stored as key value pair. Comparison of data store and the relational database is shown here. The main difference is that we use entity instead of rows to represent each object or records in the database. Now let's see how we store our data. There are total 4 categories in our data store. First is user category, storing basic information of all users. Different user entities are identified by their email. In patient category, all confirmed infected individual records are stored along with their confirmed date. Peer-to-peer and the travel category includes all necessary information to build the connection graph between users used for epidemic calculation, where the former includes contact history between people and the latter records passengers taken the same flights or trains. Detailed data structures are shown here. As the last function, we need to connect our backend to the epidemic model. Basically, the pipelines shown here. As we collect the data from data stores through fetch method, then we fill the records and only keep contact history within 14 days. All users' information and the interaction records between users are input into the model. After calculation, we will gather the updated infectious probability and update the data store. Users could also know the risk to be infected through the web page.
So for the epidemic model, we first get the input from database and then put them into our model to calculate the infection probabilities for each user. So inside our model, we need 8 input. First is people, which are all the users in our database, and then patients who are ill, and connections, how those users and patients are connected with each other. And there are also 5 levels of infection rate. For example, if we have a close contact or we have a contact that is not so close, the probabilities of being infected is different. So we set 5 levels of infection rate. To be specific, inside our epidemic model, we first store all the connections by matrix, like the figure shown on the right. We can see it's a symmetric matrix, but during our calculation to simplify, we only consider the upper right matrix because, when user 1 is connected with user 0, it's obvious that user 0 is also connected with user 1. But in our calculation to simplify our assumption, we only consider a single way of virus spreading, which is only consider how user 0 pass virus to user 1. We don't consider how they may mix together with each other. That's why we only consider the upper matrix. And then we prove each patient to see how the patients may influence the network one by one. Here, for example, we have two patients in our system. And then, so first, we only consider one patient each time. We don't consider all of them together because that would be too complicated. It's also a way to simplify our assumption. First, we see how this patient may bring changes to our system, and then we go to the second patients to see, okay, what's happening right now. So by going through everyone one by one, we can finally get all the users' infection probabilities by using this equation to calculate. So our infection rate will be 1 minus the probability you are still healthy after connecting with patient 1 times the probability you are still healthy after connecting with patient 2, and then so on. So here, one interesting thing when we are building our algorithm is that we have to consider the timestamp. For example, on March the 2nd, two healthy people were connected with each other, and on the next day, a patient came and he is connected with one of the healthy person. So our matrix will be shown like this. However, the gray point, he will be still healthy because he is protected by the timestamp. He won't be affected, although in our matrix they are connected. So that's why when we are calculating the infection rate, we have to, for each patient, we have to filter our matrix before we finally going to use that matrix to do calculation. And this part will be further discussed when we are building our test case to verify our algorithm.
Then I will introduce how we choose our test data. We will need to first input some user data to test our system. So we design a set of user data. We use the platform and data store console to input user data. We design the user's ID, password, and their relation, and so on. I will clarify what kind of data we use in the following slides. I designed a contact network to test some edge cases. The graph shows how I designed the network. The red one is infection source, and the blue one is ordinary user without infection. The first case is that the relation effect between different users is independent on the revelation date of the infection source. In this graph, the relationship between B and C is useless because the date of that relationship is earlier than the 3 infection cases joining date. The connection between B and C will not be influenced by virus. We filtered such kind of contacts in our system. The results will show in the following front-end display. The second case is that we all know the COVID-19 symptom will occur after 14 days since infection. So if one person is not infected after 14 days, then he's safe. In our data, I designed the relation like below. The infection source D will not influence E.
Next, I will take you go through the front-end techniques and our websites. As shown in the website includes mainly 3 parts. Home pages for showing your probability of infection. Forum pages where users can input information related to like peer-to-peer contact, traveling information, physical status, and the last one, network pages, where users can have a big picture view of COVID-19 social connection network. In terms of techniques, we apply Bootstrap to construct the front end. All the information shown in the home page is obtained from the backend Google Cloud Platform (GCP). Interactive networks are built based on highcharts, and the highchart retrieves datasets from Google Data Store RESTful API instead of the backend. Our website pages have registration, login, and logout pages. We don't use Google Authentication as a login tool for the reason that we don't have enough Google accounts. It can be hard for us to construct a network if we use Google Authentication. In real applications, we would suggest that we can use Google Authentication definitely. As shown on the left, it will warn you when logging as regard to your current probability of infection. On the right, there is a basic form for users to input information of peer-to-peer contacts. Also, there are There are similar pages for traveling information and physical status report. We will talk about it later. Moreover, we build a social connection network for users to reveal how close he or she is to others who get infected by COVID-19. Red nodes are infected people. Green nodes are currently healthy people or those who get recovered from COVID-19. Links represent the relationship between one and another. In such a situation, whether they can have peer-to-peer contacts or they were in the same public transportation, thicker links correspond to close contacts between them. It's also worthy to note that the construction of the network starts from the authentication of the Google Data Store, which means you have to log on through Google accounts. Then you retrieve different kinds of data sets from Google Data Store. Here we mainly care about peer-to-peer contacts than everyone's physical status. Finally, the hatchers will build the force-directed networks based on the given data sets. Finally, I will show you our future plan. Firstly, administrators surveillance. We plan to give a whole statistics analysis of the network. For example, we can use the data collected in the system to see how those infection sources influence the whole situation of the network. It's more about statistical analysis, and administrators can have more control of the networks and everyone's information. Secondly, user interface improvement. For example, we can label all those nodes with the probability of infection for better weighting based on the current network. Finally, thank you for listening to our presentation, and hope everyone can avoid stay at home and and wear masks and avoid physical peer-to-peer contact so that everyone can keep healthy during the current COVID-19 crisis. Thank you again.